Welcome to Sri Learning Academy. Let's simplify threads. When we started learning about operating systems, we talked a lot about processes. We said that a process is simply a program in execution. For example, when you open a browser, the operating system creates a process for it. That process gets memory, CPU time, and access to files or devices. Now, as we move forward into this module, it is time to zoom in a little more and talk about something that lives inside a process. That something is called a thread. To understand a thread properly, let us begin with a very simple idea. Imagine a process as a complete workplace. It has its own office space, its own files, and its own resources. Inside that workplace, there can be one or more workers doing tasks. Each worker represents a thread. So, a thread is the smallest unit of execution inside a process. While a process owns resources, threads are the ones that actually do the work. In technical terms, a thread is a lightweight unit of execution within a process. Lightweight means it is smaller and cheaper to manage than a full process. A process can exist with just one thread, or it can have multiple threads working together at the same time. Let us connect this idea with something you use every day. Think about a modern web browser. When you open a browser, the operating system typically creates one or more processes for it. Within each browser process, multiple threads run concurrently. For example, one thread may handle the user interface so the browser stays responsive. Another thread may manage network communication to load web pages, and other threads may execute JavaScript or handle background tasks. If all this work were done by a single thread, the browser could freeze while waiting for a web page to load or a script to finish. By using multiple threads within a process, the browser can perform several tasks at the same time, which makes it feel smooth and responsive to the user. Now, let us clearly separate the ideas of process and thread because this is where many learners get confused. A process is an independent entity, it has its own address space, which means its own private memory. One process cannot directly access the memory of another process. This isolation is important for security and stability. If one process crashes, it usually does not affect other processes. A thread, on the other hand, lives inside a process. All threads of the same process share the same memory and resources. They can access the same variables, the same files, and the same heap space. However, each thread has its own execution flow. This includes its own program counter, its own registers, and its own stack. Because threads share memory, they can communicate with each other very easily, but this also introduces challenges, which we will discuss in later topics like race conditions and synchronization. To make this even clearer, let us use an everyday example. Imagine a restaurant kitchen. The kitchen itself is the process. It has ingredients, utensils, and appliances. Now imagine multiple chefs working in that kitchen. Each chef is like a thread. They all share the same kitchen resources, but each chef works independently on a specific task. One chef might be chopping vegetables, another might be cooking rice, a third might be preparing desserts. Because they share the same space, they must coordinate properly, or else they might bump into each other or use the same ingredient at the same time. That coordination problem is exactly what we deal with in multithreading later. Now, you might wonder, why do we even need threads when we already have processes? The answer lies in efficiency and performance. Creating a new process is expensive. The operating system has to allocate a new address space, set up memory structures, and create a new process control block. Context switching between processes is also costly because the OS has to switch memory mappings. Threads are much cheaper. Since threads within the same process share memory and resources, creating a new thread takes less time and fewer resources. Switching between threads is also faster compared to switching between processes. This makes threads ideal for tasks that need to run concurrently and share data frequently. Let us look at a simple example. Suppose you are writing a program that downloads a file from the internet and shows progress on the screen. If you use a single thread, the program might freeze while waiting for data to arrive from the network. The user interface would become unresponsive. But if you use two threads, one thread can handle the download in the background, while another thread updates the progress bar and responds to user input. Both threads belong to the same process and share the same data, but they run independently. At this point, it is important to remember something from earlier topics. We discussed that the CPU can execute only one instruction at a time on a single core. So, how do threads run at the same time? The answer is similar to how processes appear to run simultaneously. The operating system scheduler rapidly switches the CPU between threads. Each thread gets a small slice of CPU time. On systems with multiple CPU cores, threads can actually run in parallel on different cores, which further improves performance. Another important difference between processes and threads is communication. Earlier, we learned about interprocess communication or IPC using mechanisms like pipes, message queues, and shared memory. Processes need these special mechanisms because they do not share memory by default. Threads do not need IPC in the same way. Since threads share the same address space, they can communicate by simply reading and writing shared variables. This makes communication faster, but also more dangerous if not handled carefully. Let us take a real world example from operating systems themselves. Many operating system services are multi threaded. For example, a file server might handle requests from many users at the same time. Instead of creating a separate process for each request, the server can create a new thread for each client. All threads share the same server code and data, but each thread handles a different request. This design is efficient and scalable. Now, let us summarize the key differences between a process and a thread in a simple and practical way. A process is a heavyweight entity. It has its own memory and resources. Threads are lightweight. They share memory and resources within a process. Processes are isolated from each other. Threads are not isolated from other threads in the same process. Creating and switching processes is slow compared to threads. Communication between processes is slower and more complex. Communication between threads is faster but needs careful control. One last point to keep in mind is that because threads share memory, a problem in one thread can affect the entire process. If one thread crashes or corrupts shared data, the whole process may behave incorrectly. This is why multi-threading requires careful design. In upcoming topics, we will talk about thread states, thread scheduling, and common problems like race conditions and deadlocks. Those topics will help you understand how operating systems manage threads safely and efficiently. So, to wrap this up in simple words, a process is like a container that holds resources, and a thread is the actual path of execution inside that container. Modern operating systems rely heavily on threads because they provide better performance, responsiveness, and resource utilization. Understanding this difference clearly will make the rest of the threads and concurrency module much easier to follow. That is it for this video. See you in the next one.